In this video, we're going to learn how to define continuity at a point. Let's start off with a definition of what it means for a function to be continuous at a point. We say that the function f of x is continuous at the point x equals c if these three conditions hold. First of all, we require that f of c exists. In other words, the function has to actually be defined at the point x equals c. C has to be in the domain of the function. Second of all, we require that the limit as x approaches c of f of x exists. And third of all, that limit, the limit as x approaches c of f of x, has to be equal to the function value f of c. Now, if any of these are not true, then we say that f of x has a discontinuity at x equals c. So now we want to tell whether the following functions are continuous at the given points, starting with this function f of x equals 2x plus 1 at x equals 3. So let's go ahead and check these requirements 1, 2, and 3 for this function. So requirement number 1 is that f of c exists. In this case, c is 3. We need to make sure that f of 3 exists. And well, we've got our function definition right here, 2x plus 1. So f of 3 is just 2 times 3 plus 1, which is 6 plus 1, which is 7. So indeed, f of 3 exists. That's all fine. And we also need that requirement number 2, the limit as x approaches c, in this case as x approaches 3, of f of x, which is 2x plus 1. We need to make sure that exists. And well, we can just solve this limit by direct substitution. Just plug in 3 for x here. So that's 2 times 3 plus 1, which is also 7. So that exists. That's good. And then requirement number 3, we need that limit as x approaches 3 of that function, f of x, which is 2x plus 1. We need that to be equal to f of 3. So that's something we're checking. We don't know just yet, are they equal? But we found that the limit of 2x plus 1 as x approaches 3, that's just 7. So 7 equals f of 3, you found that's just 7. So 7 does equal 7. That's indeed true. So requirement 3 is satisfied. So all these requirements are satisfied. So that means that, yes, the function f of x is continuous at the point x equals 3. Now let's move on to the next function, g of x. G of x is defined by x plus 1 if x is greater than or equal to 4, and 9 minus x if x is less than 4. And we want to tell if g of x is continuous at the point x equals 4. So all we have to do is check our requirements up here, starting with requirement 1. Does g of 4 exist? Well, g of 4, according to the function, first we have to decide, are we on this branch or that branch? So we have to look at the domain restrictions here. 4 is not less than 4. 4 is greater than or equal to 4. So we're up here on this branch, x plus 1. So g of 4 is equal to 4 plus 1, which is 5. So yes, g of 4 exists. That's good. And then requirement number 2. Requirement number 2 is that the limit as x approaches 4 of g of x exists. So what is that equal to? Well, keep in mind that g of x is a piecewise function, and its crossover point is at 4. So depending on which way we approach the limit from, the left or the right, we're going to be on different pieces of the function. So we have to evaluate both the left and right limits and make sure they match up. Let's start with the right limit. This is the limit as x approaches 4 from the right of g of x. What's that equal to? Well, from the right, we have x is greater than 4. So we're on this top branch here with x plus 1. So the limit there is just the limit as x approaches 4 from the right of x plus 1, which is just 4 plus 1, which is 5. Alright, and then how about from the left? Well, the limit as x approaches 4 from the left of g of x, now we're on the other branch where x is less than 4, so we have to use this bottom branch of the function, 9 minus x, so that's the limit as x approaches 4 from the left of 9 minus x. We just sub in 4 there, so 9 minus 4, which is also 5. So since the left and right limits are equal, they're both 5, that means the overall limit is 5. So yes, it does exist. And now our third requirement here is that the limit of g of x as x approaches 4 has to be equal to the value g of 4. And what did we find earlier? Well, we found that that limit is 5, and 5 is equal to g of 4. G of 4 is just 5. So yes, 5 equals 5. That's good. And so requirement 3 is satisfied. And that means since all of these requirements are satisfied, then yes, the function is continuous at x equals 4. Alright, last one, h of x. H of x is defined by 2x if x is greater than or equal to 1, and x plus 3 if x is less than 1. And we want to see is h of x continuous at x equals 1. Well, again, we just go ahead and check these requirements. Requirement 1 is that h of 1 exists, and we can check that by computing h of 1. H of 1, well, 1 is not less than 1, so we don't use the bottom branch. 1 is greater than or equal to 1, so we're using this top branch again. So 2 times x is 1, so 2 times 1, and that's equal to 2. So h of 1 equals 2, therefore h of 1 exists, we're all good. And how about the second requirement? The second requirement is that limit as x approaches 1 of h of x exists. So let's see, what is that equal to? Well, again, h of x is a piecewise function, and 1 is the crossover point. So depending on whether we're coming from the left or the right, we're going to be on different branches of h of x. That means we have to check the left and right limits separately. Let's go ahead and check the right limit first. Limit as x approaches 1 from the positive side of h of x. Well, when we're on the positive side, we're greater than 1. So we're going to be on this top branch here, 2x. So that becomes the limit as x approaches 1 from the positive side of 2x. And we just plug in 1 here. So 2 times 1, which is 2. So that's looking all right. And how about the left limit? The limit as x approaches 1 from the left of h of x. Well, when we're approaching 1 from the left, we're less than 1. So we're on this bottom branch here. We're on x plus 3 branch. So limit as x approaches 1 from the left of x plus 3. We plug in 1 here, 1 plus 3, and we get 4. Oh boy. So that means the left and right limits are not equal. Left limit is 4, whereas right limit is 2. And that means the overall limit does not exist. But requirement 2 is that the limit does exist. So requirement 2 is not satisfied here. We can also see that requirement 3 is not satisfied either, because this limit does not exist, whereas the function value is 2. So 3 would also be false. But really, all it takes is for one of these conditions to be false, and we see that 2 is false, so immediately we can conclude that no, h of x is not continuous at the point x equals 1. So we say that h of x has a discontinuity at the point x equals 1. Alright, let's go on to some more problems. Alright, here's our next problem. We want to determine whether the following function f of x is continuous at x equals 0. F of x is a piecewise function defined by 2x plus 1 if x is greater than 0, negative 1 if x is equal to 0, and 1 minus x if x is less than 0. Now remember our 3 requirements for the function to be continuous at a point. Let's just start by writing them down. So we need to verify the following. First of all, we need to verify that the function value is actually defined at the point. We need to verify that f of 0 exists. 2, we need to verify that the limit is defined at the point. So we need to verify that the limit as x approaches 0 of f of x exists. And 3, we need to verify that these two quantities are equal. We need to verify that the limit as x approaches 0 of f of x is equal to the actual function value f of 0. So with that in mind, let's go ahead and check these requirements. First of all, let's check, does f of 0 exist? Well, f of 0 in this piecewise function, we need to check where is 0 in these domain restrictions. 0 is not less than 0, it's not greater than 0, 0 is equal to 0. So we have to use this middle branch, which tells us that the function value is -1. So there we go, f of 0 equals -1. So that's good. That means f of 0 exists because its value is equal to -1. Now for condition number 2, we need to verify that the limit as x approaches 0 of f of x exists. So f of x is a piecewise function, again, and its crossover point is at 0. That's where all the branches change. So we need to check the left and right limits. Let's go ahead and do that. The limit as x approaches 0 from the right of f of x, well, that's where x is greater than 0, so we have to use this top branch here, x is greater than 0. So that's the limit as x approaches 0 from the right of 2x plus 1, which is equal to just plugging in 2 times 0 plus 1 is just 0 plus 1, which is 1. And then the limit from the left, limit as x approaches 0 from the left of f of x, well, from the left, we're less than 0, so we're using this bottom branch here. So that's limit as x approaches 0 from the left of 1 minus x. Just plug in 0 there, 1 minus 0, and you get out 1. So the right and left limits are equal, they're 1, so that means the overall limit does exist, it's equal to 1. So yep, overall limit exists. How about the third condition? Condition number 3, that limit as x approaches 0 of f of x, is that equal to f of 0? Well, let's see. We found out that the limit is equal to 1. So plug that in. 1 is 1 equal to f of 0? Well, f of 0 is equal to -1. Is 1 equal to -1? No, that's not right. 1 is not equal to -1. So that means this third requirement is not satisfied. And thus we conclude that no f of x is discontinuous. It's not continuous at x equals 0. So now we know how to check whether a function is continuous at a point, given the expression of the function. If the function is not continuous at a point, then we say it is discontinuous at that point, and in the future we'll gain some intuition for the different types of discontinuities that can occur.